Okay, so today is February 10th, 2021, and this is lecture 15. So what we did the last time, as we discussed it, by the way, is it clear? Can you see this clearly, my board?
Yeah.
Good, okay. So as we discussed last time, we are trying to basically doing the second moment of the area, second moment of an area, which commonly is referred to as moment of inertia. Not, of course, we don't have inertia in statics dealing with inertia, but nevertheless, we call it that way. And we said that there are two types of problems that you encounter. One is to find the moment of inertia of a general area, meaning an area that is given by a bunch of functions, okay? And then a composite shape. So we wanted to do the composite shapes today. And there are two basically tools that you have when you are going to do the moment of inertia of a composite shape. Tool number one, or A, is you go to the table in the back of your book, okay? And where moment of inertia of all these simple geometric shapes are tabulated with respect to the centroidal axes of those shapes. Okay? Centroidal axes means with respect to axes that go to the centroid of these shapes. Okay? You need that because that's the basis of your calculations. And then tool number two, which is very important to remember, is that moment of inertia of a shape about any axis that is parallel to its neutral axis, we call that neutral axis or centroidal axis, is equal to what you find from those tables for the moment of inertia about the neutral axis plus the area of that shape times the square of the distance between these two axes. Say you have, for instance, this is a triangle. You see that in that, for instance, um, table, you're given the moment of inertia about this axis, which is the centroidal axis, x centroidal axis of this shape, and this is the y centroidal axis. So if you want to find the moment of inertia of this shape about, say, this axis, I of d, would be what you find about this axis, which is tabulated in the book, I of x bar. If you go to that, if this is B, this is H, is 136 of BHQ. So you write, this is 136 BHQ plus the area of this shape, which is BH over 2, times this distance squared. It is very important that you get yourself familiarized with these two basic tools that is just a foundation to do these problems. Now, when it comes to finding the moment of inertia of different composite shapes, you have two types of problems. Problem type number one, which is more involved, is not more difficult. It's just algebraic operations would be more involved. Is you are asked to find moment of inertia about centroidal axes. That means what? You need to find the centroid of the shape, which is what we've seen before, right? And then once you find that, then you find the moment of inertia about those axes that go through the centroid. The second type of problem is easier. You're given a set of axes and you're asked to find I about a given set of axes. I will do one example of each type and you'll see how easy the whole thing is, regardless of the case. Okay, any questions though before I start? No? All right, so let's get started. All right, okay, so this is what I will do. This is the problem that I'm gonna work on because it's a good problem. I've set it up. Let's say you're given a shape like this. Is you have a square, okay, and dimensions are 20 by 20. But what you have done, you've cut out these pieces. Say this is 10 meters, this is 5 meters, and this is 5 meters. You've cut out a square piece from this corner. Then here, you've cut out a half a circle piece. So this is 3 meters. This radius is 2 meters. So this would be now 8 meters. Okay. And so this is 10 meters, 10 meters. Then here, right in the middle, you've cut out a triangular piece. So this is 5 meters, 5 meters, and 10 meters. So you've been asked to find I about X bar and Y bar. That is, you find the centroid of this shape, draw two axes, which are X bar and Y bar, centroidal axes, and find the moment of inertia about those axes. So that's the problem we're going to do. Okay? This is, the procedure is very simple. This is what you do. You set up this table that looks familiar. Okay? The first thing, of course, is that you would divide this to some sub areas. This is what I would do. I would call this half circle area 1, which is negative. I call this triangle area 2, which is going to be negative. This one is area 3, which is also negative. And this original square itself, okay, I call that area 4, which is positive. So just tabulate these. Similar to what you did with centroid. List these areas. So you have A1 negative, A2 labeled that as negative, A3 as negative, so you don't make a mistake, okay? Remember, these are negative values, and then A4. And then write down the value for each area. Area 1 is pi r squared over 2. R is 2, so it would be actually 2 pi. So you're writing these areas. So 2 pi, 6.3 negative. Area 2 is 10 times 5 divided by 2. 25, negative. Area 3 is a square, 5 by 5, also 25. Area 4 is a square, 20 by 20, that would be 400. Okay, so remember, this is basically the same table, the first part of it, that you did for setting up the centroid. So you remember the next column then would be xi. What is xi? Let's say you set up an x and y coordinate. Here, with respect to those, you're measuring the centroidal distance from each shape to the x-axis and then the y-axis. This is from the to the x-axis. So for xai, this is its centroid, right? So the distance from that centroid, right, to y-axis, that is xi. This distance, if you remember, if you have a circle, this distance was 4r over 3 pi. So it would be 4 times 2 divided by 3 pi. You see that if you calculate that, comes out to be 1.15. So this is 1.15 minus 20, that would be 18.85. For 2 is right here, is 1/3 of a distance from here, 1/3 of a distance from here. So 1/3 of 5 and 1/3 of 10. This would be 3.33. This would be 1.67 or almost 1.7. Okay. So distance from this is 1.7. This is 10. I'm sorry. This is 3.33 from y-axis. So this is 3.33. For this guy is right here, which is 2.5 and 2.5. So this distance 2.5, this is 15. So this is would be 17.5. And for this guy, this is the centroid of this square. So that is 10. Now, the next column, you remember, XIAI. So just multiply this by the corresponding area. So this would be 118.4. Area is negative, so this would be a negative value. This would be product of these two, 83.3, and that is negative. 17.5 times that, 437.5, also negative. And this one 10 times that, 4,000. So if you add these up, okay, divided by the summation of these, okay, which you can find, that would be sum of these divided by this sum. This sum is 3,361. If you add these up, this is 350 minus uh, 6, so it would be 344 or 333.7. Divide this by that, you get x bar, which gives you 9.8 meter. So this is where the centroidal x is located at the distance of 9.8 from here. So would be along this line. This is x bar, which is 9.8 meters. okay? Now, y bar is located along this line. To find that, you continue. Find the distance from each centroid to the y-axis, for this y-axis. If you do that for this guy, okay, I'm sorry, would be from x-axis. If you do that for this one, would be from here to here, which is 10. For this guy, would be 1.7 plus this, you're measuring from x-axis, so would be 11.7. For this one would be from here to here, which is 15 plus 2.5, 17.5. And for this one would be 10. Now, next column, similar to what you did here. This times the corresponding area. So you just find the product of these two, tabulate them here. So this would be 63 negative. This would be 291.8 negative. This would be 937.5 negative, and this would be 4,000. So what you do here, if you add these up, okay, so it would be 3,207 divided by that. That'll give you y bar, comes out to be 9.3 meters. So y bar, okay, is, in other words, along this line, you go 9.3. This is 10. So roughly here, and this gives you the, okay, this is y-axis of centroid. This is the x-centroidal axis. So you have established those two axes that the problem is asking you to find the moment of inertia about those. Okay? This is what you do. As the first step, you just simply find the moment of inertia. Let's say you want to find moment of inertia about this axis, right? So what you do, you set up a column, and in that column, you tabulate the moment of inertia of each shape about its own x centroidal axes. That is, for instance, for this one, this is the x centroidal axis of this shape. For this one, this is the x centroidal axis. For this guy, this is its x centroidal axis. For this guy, so I need to find a moment of inertia of each shape about these axes. So you go to that table, you see for this guy, this half circle, moment of inertia about this axis is tabulated as 1/8 of pi r to the 4. Okay? So 1/8 pi times 2 to the 4, and that gives you 6.3. This is a negative area, so that's a negative value. For this guy, you go to the table, you see for a, and I did that here actually, for a triangle, moment of inertia about this axis is 1/36 of this base times height cubed. So it's 1/36 of the base, which is 10 times height cubed. Okay, that gives you 34.7. okay? For this guy is 1/12 of B base, which is 5 times height cubed, which is also 5. That, you evaluate that, you get 52.1, which is also negative, okay? And for this guy is 1/12 of base 20 times height cubed. Height is also that. So that gives you 13,333. Okay. So these are the moment of inertia of each shape about its own central axis. Just leave it as is. Tabulate them. That's not what we need. We need the moment of inertia of each shape about this axis. So you need to find a moment of inertia each shape of this axis and add them up. What does that mean? That you need to, this is a parallel axis. This axis is parallel to the central axis of each shape, right? So you need to add the moment of inertia of each shape about its own central axis, add to it the area of the shape times the distance from that central axis to the corresponding central axis of each shape squared. So you just tabulate that. What does that mean? You write that 6.3, okay, and add the distance from here to here. What is this distance? This is 9.3 meters. What was here? This was 10. So this distance would be 0.7. So I just add the area of that, which I have it here, okay? 6.3 times 0.7 squared, and write it here. That would be 9.4, okay? Same thing here. Just write this value, 34.7, add to it the area of this shape, which is 5 times 10 divided by 2, you have it here, 25, times the distance from here to here. This is 1.7. In other words, this was 11.7. You had that, 11.7. You subtract 9.3 from it. That would be 2.4 squared. So this is from here to here. This was 11.7. You had that, minus 9.3. So you evaluate that. That gives you 174.3.
Professor, I have a
Negative.
quick question.
Sure.
Where did the 9.3 come from?
You calculated that, right? That was the,
yes.
right. This was this distance from the centroid axis to here. Any other questions? All right. So go to A3. You want, again, to add what you have here, which is the moment of inertia of this shape about its own centroidal axis, plus this is from here to this. This was 17.5. You see? Subtract from it 9.3, that would be 8.2. So you write area times 9.2 squared, and that will give you the value of 1,733.1. So I should have probably drew that line here. This is for A3, okay? How about for this guy, A4? Again, you have this, what you have here, 1,333 plus its area, which is 400, times the distance from the centroid here to here. This is 10 minus 9.3. 10 minus 9.3, 0.7 squared. Calculate that, gives you 13,529. Now, all you have to do, just add these up, and that will give you 11,612 meter to the fourth, which is the moment of inertia of this shape about this centroidal axis. Okay? Any questions? No? So now you want to find a moment of inertia about this. So what you need to do, you need to find a moment of inertia of each shape about its own y centroidal axes, and then add to it the area times the square of the distance from its centroidal axis to the new axis. That's it. So first you need to write these, right? I of each area about its own central axis. So you go again to that table, you see that moment of inertia of this shape about this axis is tabulated, okay? That is 1/8 pi r to the 4, so you just write it down, 6.3. For this guy is, with respect to this, is 136 of the base parallel to that, 136 of 5 times height cubed. So if you calculate that, that comes out to be 138.9 negative, okay? Because that area doesn't exist. Now, for this guy, for the third one, which is this, same thing. 1/12 of base times height cubed, which is going to be the same because it's a square. So these two come out to be the same, 52.1. Okay. And for this guy, 1/12 of this base times this height cubed, again, this is a square, so height and base are the same, so it comes out to be the same. So it would be this, 13,333. Now, the last column, you want to find a moment of inertia about I, this one. So you have these, just add to them. Let's say, for instance, this one would be 6.3 plus the distance from here to here. You had this distance already, which is your what? Which is your X bar, 18.85 minus 9.8. Okay, so 18.85 minus 9.8, that'll give you 9.05. So it would be this area, which was 6.3 times 9.05 squared, and that will give you 520.65 negative. How about for the second one? It is this, you just add 138.9, which is a negative value, add to it another value, which is the area of this shape, which is 25 plus 25 times the distance from here to here. Okay, this is 9.8. This is 3.33. So that would be 6.3 squared. If you evaluate that, gives you 1,182.2. Okay, so that's the moment of inertia of the first one, moment of inertia second one about this axis. How about the third one, this guy? At this 52.1 plus the area, which is 25 times this distance squared. Okay, what was this? This was 17.5, right? In other words, you had this was 27.5 minus 9.8. Okay, that would come out to be 7.7 squared. So if you calculate that, you get 1,534.4. Okay, so that's for this one. Okay, the last one is this guy, would be 13,333 plus its area, which is 400, times this distance, which is 10 minus 9.8. So it's only 0.2 squared. And that gives you 13,347 positive. Now, if you add these up, that you're adding up moment of inertia of every shape about the centroidal axis, and you get 10,109.8 meter to the 4. Okay, so that's, you found the moment of inertia of the shape about this axis and this axis. As easy as that. Any questions? No? All right. If not, let me do another problem. Okay. So let me, before doing that other problem, there are a few shapes that we used here from the table. Let me show you again. If you go to those tables, you see that moment of inertia versus this shape about X is tabulated. If this is B, this is H. If you want moment of inertia about this guy, would be 136 of HB cubed. Okay. If you want the moment of inertia about this one, would be different. It's tabulated. I don't have it here. So for a rectangle BH cubed, moment about x-axis is this. But if you want about its y, would be 1/12 of HB cubed, right? So that's what we were doing. Okay. And those are what are tabulated. Okay. So let me do another problem here, okay, which is the second type of problem. So I write type 2 problem. So in this case, you're asked to find moment of inertia about an existing XY coordinate. So I'll do a relatively simpler problem, but the concept is the same. Let's say you have a rectangular shape like this. This is 108 meters. This side is 60 meters. So these are the two central axes of this shape. We have cut out at the distance of let's say 22 meter from here and 14 meters from here. We've cut out a triangular shape like this, okay? So this height is 18 meters and this is 18 meters. So in other words, this would be 72 meters, this is 22 meters, and this is 14 meters, okay? So we want to find the moment of inertia of this shape about these two axes that are given, not the centroidal axis of the shape, but these two axes. This type of problem is easier, less operation involved. Why? Because you no longer do you need to find the centroid of this shape. You don't need that. All you need is the distance from the centroid of each shape to these axes that are given. So, but as a first step, obviously, you divide this into sub areas. Since I like right angle triangles, they're easier, the tabulated value is easier to find. So I would divide this into shapes like this. I call this A1 negative, A2 negative, and then this rectangle would be A3, okay? So in this case, this is the table you set up. All you need is this. You tabulate those areas, obviously, A1 negative, A2 negative, and A3 positive, right? Write their corresponding areas in this column. So for area 1 is 18 times 72 divided by 2, 648 is a negative area, remember? Same thing for this guy, 648. A3 is 108 times 60, would be 6,480. Now you go directly find the moment of inertia of this shape about its own centroidal axis. So what is the moment of inertia of this shape about its centroidal axis? Central axis, again, is 1/3 from here and 1/3 from here. This is 6. This would be 1/3 of 72 is 24. So it would be somewhere here. Same thing for this guy. Okay, 6, and this is 24. Moment of inertia of this one, A1, about this axis. In other words, you're trying to find this. This is B, this is H. Moment of inertia about this axis is 136 BHQ. So it would be 136, base is 72, H is 18 Q. Calculate that. That gives you 1,087.5. And this is negative because this area doesn't exist. How about for this guy? Moment of inertia, okay, about this centroidal axis, which is basically kind of reversed. That's it. Okay, so you're trying to find a moment of inertia about this axis with respect to its centroidal axis is again 136 of base, which is the same, 72 times height cube. So it would be the same value. How about for this guy? Is a rectangle 1/12 of base. So you're finding the moment of inertia about this axis for this guy. 1/12 of base, which is 108, height cubed, 60 cubed. And that'll give you, I didn't do that, I better do it. Okay, I did not calculate that. Let me do it here. That would be 60 would be what a large number. Let me double check. 60. So we have 3,660 times 108 divided by 12. Comes out to be a very large number. 1,944,000. But that's not what you want. You want the moment of inertia of this shape about this axis. So you need to write the moment of the distance. You need to find, in other words, you need to add these values plus each corresponding area times the distance from the centroid of that area to this axis. Okay? So you have this is D1, that this is 30 plus 6. So this is 36. So all you do, you write this 1,087.5 plus the area, which you have, 648 times 36 squared. Okay? And let me write that down. I had not calculated that before, but I'm going to do it now. Okay? Okay, plus 1087.5. That's also a large number. 840,895.5. This is the moment of inertia of this shape about this axis. How about this guy? Would be the same 10875 plus distance from here to here. So this distance is going to be 30 minus 6, so it would be 24. So plus that area times 24 squared. So let's write that down. Evaluate that. Okay? Plus 1087.5. That gives you 374,335.5. Okay? And that's negative. Okay? So let me do that again. Double check. Right. Now, moment of inertia of this shape, which you have, about this axis. What is the distance from the centroidal axis of that shape to here? Is this 30. So you write 1,944,000 plus the area, which is 6480 times 30 squared. So let's see how much that would be. What a large number. Okay. So that'll be 6,480 plus 1,944,000 That would be 7,776,000. Now, all you need to just add these up. These are negative, so I will add them up. 374, 335.5, 840, 895, comes out to be 6,560,769 meter to the fourth. So the moment of inertia of this shape about this axis is this. So you can see that the much fewer operations are involved in this case. That's it. Let me repeat myself. What you need are two tools. Moment of inertia of each shape about its own centroid or its own central axis, which you find it from those tables. Remember the parallel axis theorem. Find the moment of inertia of each shape about its own centroidal axis. And to find the moment of inertia about another axis that is parallel to it, just add the value that you find based on that table. Okay? Add to it the area of that shape times the square of distance from the centroid of that shape to this axis. That's it. For type 1, of course, you need to set up those axes. So you need to locate the centroid of the shape and find those two axes, and then find the moment of inertia about those axes. Type 2, you're given a set of axes. You don't need to find the centroid of the shape. Just find the moment of inertia of each shape about its own centroid, and then about these axes that are parallel to it. That's it. Very easy. Any questions?